Last time we came up with a rather powerful tool called the Taylor series, and remarkably, it was developed from a fairly simple theorem called the mean value theorem. Now, this time we're going to see if we can't get a little bit more of a handle on the Taylor series and try some examples. Now, the Taylor series is going to be with us for the rest of the course, and its ability to create predictors and analyze the error of any approximation we'll find to be essential in a variety of tools that we'll be discussing and covering in the future. So let's get a little practice on that. Let's try looking at a simple function called e to the x. You should be all very familiar with that. This function has the very nice attribute that you can differentiate it any number of times you want and you get e to the x back. So we will use it in the Taylor series, and we will evaluate the sum, the series, around x0 equals 0. So here's our derivatives, and we could just go on forever, just differentiating it to our heart's content. And we'll express any one of those derivatives, we'll call it the kth derivative, as f to the superscript k in parentheses, and it will still deliver e to the x. So we'll apply that into our Taylor formula, evaluated at 0. And this is what we will get, or if we simplify it just a bit, we get this fairly straightforward sum of reciprocal factorials times a polynomial power with an error term evaluated at an unknown point between 0 and x. So here's our formula for that. So let's try our Taylor series with a simple f of x equal e to the x. We're only going to use 3 terms past the constant term. We will use x0 equal to 0 to be our anchor point, and we will evaluate the function at 0.85. So it'd be nice just to make a little table where we have the index number, the function and its derivative, and the Taylor terms which are summed, and the result of those terms when x equals 0.5. So you can see that and plug that all in for yourself. And if you add up these terms, you get something close to 2.31. So if you go back to any computational tool of your choice, you'll discover that e to the 0.85 is closer to 0.2334. So there is a true error between the correct value and this truncated sum. And we could calculate that true error right here. So if instead we chose to use the 4th Taylor term, and we chose to plug in zeta, the unknown zeta, to be 0.85, we would get this E4 term of about 0.05, clearly bigger than the true error. We know that the exponential is a monotonic increasing function, and therefore the largest value we're going to get out of e to the x is going to be at its rightmost point within the interval that we're constrained to. So this is as big as that error could ever get, and in fact we're seeing that it worked quite nicely. Let's try the same approach on a different function. Again, one we're familiar with would be the sine of x. We'll continue with 3 terms past the constant term. We'll continue to evaluate the sum around 0, and we will choose to evaluate the function at pi over 6. So we're developing the same table, but as you're already familiar with the sines and cosines, when you differentiate them, they not only flip back and forth between sines and cosines, but they change sign as well in pairs. And you can check that by looking at the derivative. If you evaluate any of the terms that have a sign in them, then you're going to get the sign of 0, which is 0, and therefore every odd term that you choose to calculate will be 0. Not too interesting. The only ones that are contributing anything are the odd numbered indices. So we end up trying that. We get a sum of pretty close to 0.5. And again, if you check your calculator, you'll find that 1/2 is the actual correct answer. So the difference between the true answer and our calculated answer is really quite close. You can see that there's very little error going on. Now it looks like I have a typo here. I thought we were supposed to have e sub 4 in this because we have 3 terms and we're supposed to use the next one to create the error. But this actually is not a typo. The reason we're jumping to E5 is we know that all even terms are 0. And therefore, we essentially did use 4 terms in calculating this series. And the error, therefore, really is the 5th term. And that's partly why this thing does pretty well in convergence. Let's talk about something I like to call misbehaving series. Well, a misbehaving series, in my opinion, is one that wanders off endlessly without bound. Sometimes we say it wanders off to infinity. That's probably not the best way to put it because infinity isn't really a place, but you get the idea. So if we added up, in this example, 1 plus 1/2 plus 1/3 plus 1/4, on and on and on, you would think it would settle down and stop somewhere, but it actually doesn't. It keeps growing without bound. Now that can get you in deep yogurt when you're programming because many of the methods we'll use will compare the last 2 terms for closeness. We'll be interested in what we'll call the relative error between the last 2 calculated points. Now in this case, you can make that just about as small as you want and fool yourself into thinking that you can stop somewhere and actually get something pretty close to the right answer. So we will have to be careful with these misbehaving series as we are looking at them in the rest of the course. Okay, so that's just a warning. On the other hand, you could have something that's called an alternating series. And as it turns out, as long as we're flipping the signs back and forth, this series will converge. Now, just as a side note here, this is a really convenient method to describe plus and minus ones. We are going to use that kind of notation a lot, so you need to get used to it. If you just try plugging k equal to 1, then 2, then 3, you can see that this term is going from +1 to -1 to +1 to -1. And these kind of terms show up quite a bit in many contexts of mathematics. Well, if we apply this alternating series to what used to be our misbehaving series, in other words, we still add up 1 plus 1/2 plus 1/3, with the exception that we change the sign every other term, well, then this will converge and produce a bounded value. Okay, so let's get our hands dirty. Let's try doing a homework that we can use to play with the Taylor expansion. In problem 1.2, now this is ordinary problem, which means that it's the first of the 2 sections of problems that you'll have in that section of the book. We're going to take the log of 1 plus x, and we're going to do the same thing we just did on the examples. We'll take 3 terms past the constant and see if we can write down this cubic polynomial that will be a reasonable approximation for the log of 1 plus x. That's worth 5 points. Then code it up in just P code, your pseudocode, again to 3 terms. You don't need to turn that in, but use that as a basis to write MATLAB code that you will turn in. Put in 0.85 as an argument for x, and run your code, and we'll see what you get, and you'll turn that into me. So then we'll work problem 5 in the same section. Again, we're going to be doing a Taylor expansion, but on the hyperbolic cosine. We're going to use 0 as our anchor point, and then we're going to evaluate the hyperbolic cosine of 0.7. This time we're going to use 4 terms beyond the constant value, so just a little bit more. And compare that to the actual value you might get off your calculator or whatever computation tool you'd like to use. Finally, if you'd like to earn 5 extra points, go to problem 8. Again, you're going to go back to e to the x, and the question will be is how many Taylor terms past the constant would I need in order to get 15 significant digits of accuracy. Don't just guess, I need some mathematical justification for this. This is not a MATLAB program. This one is a handwrite, which you scan and turn it into me as a PDF file. So with that, we'll finish up this section, and good luck, and I'll look forward to seeing you next time.